Hi everybody, welcome to a new unit. In this unit we're going to be studying equilibrium, when things seem to be equal with each other. We are going to be talking about, in this particular video, equilibrium and Kc, and then type 1 equilibrium problems. Let's get started. So there are two types of reactions, well, amongst the many types of reactions, but that we're going to be discussing here. Reactions that go to completion and reactions that don't. So some chemical reactions go to completion, and that means that the reaction produces product until all of the limiting reactants are used up. So it goes in one direction only. This is what happens with the dissociation of a strong acid. HCl will convert into H plus and Cl minus. These reactions are represented with a single arrow to show that the reaction proceeds in only one direction. So some reactions will completely make products and that's it, and they're done. However, many chemical reactions are reversible, such as the evaporation and condensation of water. Water liquid will turn into water gas, and water gas will turn back into water liquid. Or the dissolving and precipitating of a salt. Salt, NaCl solid, will turn into Na plus and Cl minus, and Na plus and Cl minus will turn back into NaCl solid. These reactions are often represented with a double arrow to indicate that the reaction is proceeding in two directions at the same time. One is happening and the other is happening at the exact same time. So these reversible reactions eventually reach a point where the concentration of the products and reactants no longer change over time. This point is known as equilibrium. Let's look at a graph to show you what I'm talking about. So at the beginning of a reaction, the concentration of reactants are high because there are reactants in the container. The concentration of products are low, or zero, because the products haven't been produced yet. So the reactants are going to decrease over time because the reactants are being used up to make products. And the products are going to increase over time because the products are being produced. At some point, as the reactions are decreasing and as the products are increasing, their concentrations will change no more over time. At some point, you will see that these lines are now flat. These lines aren't moving in any particular direction. This point is called equilibrium, when the concentration of the reactants and products no longer change over time. Now, in this first graph that we were just looking at, the products at the end of the reaction, or at equilibrium, had a greater concentration than the reactants. It's also possible that the products are produced over time, the reactants are used up over time, and at equilibrium, there's a greater number of reactants than there are products. Both of these are equally valid ways to see a reaction proceed. At equilibrium, the concentration of reactants and products can even be equal, but this is rare. Typically, there'll be more of one or the other. Please note that these reactions must occur in a closed system or a closed container so that the reactants and or products don't react with anything other than each other. So we've just got reactants and products. We're not worried about open to the surroundings. So because the concentration of the reactants and products do not change at equilibrium, an equation exists that can relate the concentrations of reactants and products to each other. The ratio of products to reactants is known as the equilibrium constant, or KEQ, EQ for equilibrium. KEQ, the equilibrium constant, can actually be expressed in a couple of different ways. And the first one we're going to be looking at is what we generally know as plain K, also known as Kc. Kc, so the equilibrium constant based on concentrations. The C is for concentrations of the gaseous or aqueous products and reactants. So the formula is K is equal to the concentration of the products raised to the power of their coefficients divided by the concentration of reactants raised to the power of their coefficients. So first off, let's look and see, do you see these brackets that are right here? These brackets represent concentration in the units of molarity. So the fact that we have brackets means that we're talking about concentration in the units of molarity, and then raised to the power of their coefficients. So if I had, for example, 2A plus 3B makes C, my product is C, so K would be equal to the concentration of C divided by My reactants are 2A and 3B, so it would be A squared times B cubed. I need to have brackets because I want to represent the concentrations of A, B, and C, and then raised to the power of their coefficients. So if it's 2A, it's raised to the power of 2, or squared. And if it's 3B, it's raised to the power of 3, or cubed. Also take note here that these guys are multiplied, not added. They're multiplied together, not added together. Even though within the reaction they're added, in the K equals expression, they are not added, they are multiplied. An example. Given this reaction, write the equilibrium constant expression. So first of all, I need to know what's the products and what's the reactants, because it's going to be products divided by reactants. So K equals, and the equilibrium constant expression, this tongue ties me a lot. A lot of times I'm just going to call it the K equals expression. Let's write the K equals for this reaction, because that's a lot easier to say. So anyway, starting with the products, we said that that was NH3. It's going to be NH3 in brackets, has to be in brackets to represent concentration, raised to the power of 2, or squared, divided by the reactants, so that's going to be N2 times H2, and the H2 is going to be cubed because there's a 3 in front of the H2. That is the equilibrium constant expression right there. Essentially, that's the equation that you're going to plug numbers into. So given the following equilibrium concentrations at 127 degrees C, calculate K. First of all, this temperature is not necessary for the problem. K will change when temperature changes, but as long as the temperature is constant throughout the problem, the temperature is not actually important. So we're going to calculate K by plugging into the equation that we just solved for. K is equal to the concentration of NH3, 3.05 times 10 to the negative 2, that's 0.0305, and then that's going to be squared, because we said NH3 squared, divided by N2, 8.47 times 10 to the negative 1, 0.847, and that's not raised to any power because there's nothing next to the N2. And then times H2, 3.05 times 10 to the negative 3, 0.00305, raised to the power of 3 because it's NH3 cubed. So then I'm going to get out my handy-dandy calculator, 0.0305 squared, and I've got 9.3 times 10 to the negative 4, and on the bottom I have 0.00305 cubed times 0.847, and I get 2.4 times 10 to the negative 8, and then if I divide those two, I get 3.87 times 10 to the 4. So that is my K for this problem. One cool thing about K is that it is dimensionless. There is no unit at all. So don't even have to worry about a molarity or a volume or anything. It's just plain number only. Let's look at another example. In fact, why don't you try this one on your own? Pause the video here. Okay, so I hope you did that. Let's look. Calculate K, so the first thing we need is a K equals expression. Our products are NO squared times Cl2, and our reactants are NOCl squared. So now, all I'm going to do is plug in the values that they give me. NO is 4 times 10 to the negative 3, 0.004, and then that's squared. The really big thing, the most often missed, is forgetting to include those squares and cubes from the coefficients that you said at the beginning of the problem. You notice them at the beginning, but it's easy to forget them once you're plugging numbers in. So just pay attention to the K equals expression that you already wrote. And then we have Cl2. Let me get some of that green out of there. And let's look at Cl2. 1.52 times 10 to the negative 3, 0.01, nope, 0.00152, and then divided by NOCL squared, 0.396 squared. Don't forget the square. We have a square here, so we need to have a square here. I'm going to even do that in green so we remember and we see it and we know it's there. So then all you got to do is solve. 0.004 squared times 0.00152 gives me 2.43 times 10 to the negative 8, and then 0.396 squared gives me 0.157. So when I divide 2.43 times 10 to the negative 8 divided by 0.157, I get 1.55 times 10 to the negative 7 as my final answer with no unit necessary. Okay, so if you didn't start Part B, go ahead and do Part B now on your own. Alright, so now we should all be looking at something on Part B that you have attempted yourself. Notice how K changes for the reaction in Part B. This time the reactants are NOCl. Sorry, products are NOCl. Those used to be the reactants. And this time the reactants are Cl2 and NO, and those used to be products. So what's the relationship between the original K and my new K? Hopefully you're seeing that they are reciprocals of each other. In other words, flip the fraction upside down. So, if you took this answer that we got earlier and turned it into a fraction, if you really take any number and turn it into a fraction, what you're going to do to that number is essentially just, would you all agree with divide by 1? Which means that since the reaction has been reversed and K has been inverted, this is going to end up being 1 over 1.55 times 10 to the negative 7. You don't have to type in all those numbers in again upside down. In fact, if you have this 1.55 times 10 to the negative 7 stored in your calculator, there's an inverse button that looks something like this, x to the negative 1 or 1 over x. And you can just hit that button and it'll automatically give you your answer without having to type in 1 divided by your previous answer. And you end up getting 6.45 times 10 to the 6. And that is your K, and that's it, and you're done. Now these problems that we've worked so far are called type 1 problems because all the information is given for you, and all you have to do is solve for K. Or sometimes 2 out of 3 concentrations and K is given for you, and all you have to do is solve for another concentration. So a type 1 problem is just a problem where all the information is given, just solve for the one missing piece. In our next video, we're going to get to type 2 and type 3 problems where there's more than one missing piece, and it'll be a little bit trickier. I hope you'll see me then.